Hello and warmly welcome to everyone. Let me introduce myself. My name is Bekir. I'm working as a postdoctoral researcher in the multi-objective optimization group at the University of Jyväskylä in Finland. In this presentation, I'm going to talk about challenges in data-driven interactive methods and our multi-agent architecture to address these challenges. Let me give you a brief outline of my presentation. I will start with the basics of interactive methods. Then I will list the challenges in data-driven interactive multi-objective optimization. Next, I will present our proposal of the multi-agent architecture and the agents inside the architecture in details. And finally, I will summarize and conclude my presentation. I would like to give you some basic information about interactive methods. While solving a multi-objective optimization problem with an interactive method, a decision maker takes part in the solution process. They provide their preference information and method generates solutions based on the preference information. This continues until the decision maker is satisfied. In this way, decision makers can direct the interactive methods to find the most preferred solution. Many interactive methods have been proposed in the literature. They differ from each other, for example, in the way the decision maker expresses preference information, how information is exchanged between the decision maker and the method, and what kind of subproblems are formulated to get solutions based on the preference information, and what is the stopping criterion. These are the key elements as difference between several interactive methods. If we look at the real-life decision-making processes, we can distinguish the solution process into two phases called the learning and the decision phase. In the learning phase, decision makers try to understand the problem structure, and for this they explore different Pareto-optimal solutions and find the region of interest. And in the decision phase, decision makers refine the solutions in the region of interest and aim to find the most preferred solution. As said, many interactive methods have been proposed in the literature. They follow the traditional mechanism of interactive methods that was proposed in the early 70s. Nowadays, there is a huge amount of data accumulated from several application fields. We need to deal and solve complex and data-intensive problems. If interactive methods do not support decision makers while solving this kind of complex models, they can easily be overwhelmed with information and providing preference information becomes difficult for them. This situation brings new challenges. Traditional solving mechanisms should be enhanced to address these challenges. So we need to provide novel tools to solve the issues that are currently available because of the data-intensive and complex problems. The first challenge is the computational challenges. In real-life applications, objective functions can be expressed as a mathematical function formulations or can be derived from the simulation data, or real-world data can be utilized in the multi-objective optimization problems. Solving this kind of data-driven problems may be computationally expensive, and deriving candidate solutions may take a long time. However, in interactive methods, waiting time of the decision makers between iterations should be reasonable, since they have some time limitations or some deadlines to reach. The second one is data uncertainty challenges. If we are dealing with the data, it is highly possible that we need to pre-process to make the data available for optimization. And this available data might be incomplete and we need to fill those missing data. Or there might be some estimation errors or imperfections. Or data has natural uncertainty such as unknown feature that should be incorporated in the solution process. Turning our attention now to cognitive challenges. If the decision maker is solving a many objective optimization problem, the decision maker may be overwhelmed with the information that method provides. The amount of the information between the decision maker and the method should be adjusted according to the human cognitive capacity. In the beginning of the solution process, the decision maker might have incomplete or uncertain preference information. This causes the decision maker might give contradictory preferences during the solution process. And as a cognitive challenge, we can also say that every decision maker might have their preferred way of providing preference information. As said, different decision makers may prefer different ways of providing preference information. In experience, decision makers may need support when selecting the interactive method before the solution process is started. Some methods are better for some particular problem types. Also, there are some different needs in accordance with the phases of the solution process. We know that some particular methods are suitable for learning phase or some others are better for the decision phase. So there should be some assistance to change the interactive method during the solution process based on the needs of the decision maker. These challenges motivates us to make the interactive methods more appropriate for the needs of data-intensive and complex multi-objective problems. As I mentioned before, the decision maker should be in the center of the solution process. The interactive solution process should be shaped based on their needs or their preference information. They should feel that they are controlling the solution process. So, we need to support decision makers by making the interactive methods understandable. This is possible if we change our focus to user friendliness and explainability. We believe that there is a need to support decision makers to select the better method for their needs. And also, if they provide the preference information in their preferred way, they feel more comfortable and the cognitive burden might be lesser. Because of these needs, we need a system that includes multiple interactive methods, and this system should support the decision makers in the mentioned ways by using the strengths of each interactive method in the system. With the help of the multiple intelligent agents, we can provide a user-friendly and explainable interactive solution processes. It is possible to hybridize interactive methods and use their strengths in the solution process if needed. Now, it is time to present the multi-agent architecture that we proposed to address the challenges I listed before. This figure shows our proposed architecture. As you can see from the top of the architecture, each interactive method is operated by a dedicated agent. This makes the hybridization straightforward and one can add a new interactive method to the system easily without changing the other elements of the architecture. These agents work on the shared environment to reach the overall goal. In our system, environment consists of multi-objective optimization problem, surrogate models, preference information, solutions, and the necessary data. First, the multi-objective optimization problem is constructed. If surrogate models are needed in the optimization model, this process includes creating surrogate models as well. We support the decision maker by utilizing preference models and preference learning techniques. We keep candidate solutions in a shared archive to make them available for other agents if needed. I would like to emphasize that our purpose is to use the strengths of each interactive method, reducing waiting times of the decision makers in the solution process, supporting them to decrease their cognitive load, and make them feel being in the control in the solution process. Let me elaborate further on each agent now. Problem agent is responsible to construct the optimization model based on the given problem description file. We assume that this problem description file is prepared by an analyst before the solution process. If we have only data rather than mathematical function formulation for the objective, the problem agent requests a corresponding surrogate model from the surrogate agent. If we have computationally expensive objectives, the problem agent asks computationally inexpensive surrogate models from the surrogate agent. Otherwise, the optimization model is constructed simply on the derived objectives, decision variables, and constraints from the problem description file. The next agent in the architecture is the surrogate agent. This agent is responsible to select the best modeling technique and trains the selected model by using the available data. It creates surrogate models based on the type of the request from the problem agent. This can be a model for representing an objective which has no mathematical function formulation, or a computationally inexpensive model, or a surrogate representation of the Pareto front. The surrogate agent also updates these models if needed. If the surrogate model is built for computationally expensive function formulation, it updates the surrogate model based on the candidate solutions which are obtained in the solution process. If the surrogate model is built for the data, the surrogate agent updates the model when the new data is available. We are updating surrogate models to increase the accuracy and the quality of the models during the solution process. Let's move on the solution pool agent. We want to hybridize interactive methods to use their strengths. For this purpose, we need a shared archive that includes obtained solutions so far. The solution pool agent is responsible to manage this archive. It combines the obtained solutions with the previously generated ones and eliminates dominated solutions. In this way, interactive method agents cooperate with each other by reaching best solutions obtained so far. If the decision maker wants to select previously generated solutions, the solution pool agent provides these solutions as well. The agent in the architecture is the coordinator agent. We can see this agent as a manager of the system. It makes connections between the other agents and manages the environment that should be shared with others. It selects the interactive methods based on the preferred preference expression style of the decision maker. During the solution process, in early iterations, it suggests methods that are known better for the learning phase, and later it suggests methods for the decision phase. This agent monitors the solution process and uses some quality indicators to see the performances of the interactive methods. Based on this evaluation, it can suggest some other interactive methods during the solution process. We want to give every opportunity to make the solution process better, but the decision is always given by the decision maker. The preference agent lists the preference expression styles according to the methods that are included into the system. It takes the preferred way and informs the coordinator agent. And during the solution process, it selects subset of the solutions to be shown to the decision maker to decrease the cognitive burden on the decision maker. It observes decision maker's behavior by keeping the preference information and creates a preference model by using some machine learning techniques. If the new preference information has inconsistencies with the created model, it gives a notice to the decision maker that they provide contradictory preference information. And if there is a suggestion from the coordinator agent to switch the current interactive method to another one, it informs the DM during the solution process. Up to now, for this agent, I have talked about one solution process, but this agent can be utilized for further decision-making processes if the optimization model is similar to previous one. The created preference model in the previous solution process can be used to decrease the amount of needed information and also reduce information exchange with the decision maker for further solution processes. This makes the cognitive load on the DM smaller, lesser, and supports them while providing preference information. As I said before, each interactive method is covered by a dedicated agent. Interactive method agent provides an interface to manage the connection between the system and the interactive methods. It includes method-specific details and knows what is needed for the underlying interactive method it has. It takes inputs of the interactive method from the coordinator agent and provides solutions once the algorithm obtains the solutions for that iteration. I would like to summarize with benefits of the architecture. With the help of the agents inside the architecture, we are reducing waiting times and cognitive burden set on the decision makers. Besides, decision makers can be able to switch between methods based on their needs during the solution process. Additionally, decision makers can provide preference information in their preferred ways, and they are assisted with the help of the preference agent. In conclusion, let me sum up my main points. We try to incorporate multi-agent systems into the interactive data-driven solution process to address the challenges that we listed for data-driven interactive methods. We are aware that this study is giving a roadmap, and our goal is taking feedback from the research community in the multi-agent field. And we also aware that each agent deserves several publications to build the architecture alive. As a next step, we want to study on the preference agent to make the human-agent interaction in explainable ways. And our long-term goal is to utilize this architecture in our Destiny framework, which is an open source framework developed for using and experimenting with several interactive methods. Thank you all for listening. It was a pleasure giving this presentation today. Please feel free to ask your questions. And now we have a time to discuss, and I will gladly answer your questions if you have. Thank you again.